instance-based versus model-based learning. So the question here, what survives training? Here's another fundamental split. After the model is trained, what does it keep? Instance-based learning keeps everything. Every single training example is stored. At prediction time, it finds the most similar stored examples and uses their labels to make decisions. K-nearest neighbors is the canonical example. Model-based learning compresses the data into a set of parameters: weights, thresholds, coefficients. At prediction time, it applies a mathematical function to the input. It doesn't need the training data anymore. Logistic regression is the canonical example here. Let us visualize this one and understand it. So as you can see here, we have the instance-based versus model-based learning. So for the instance-based, we use the K-nearest neighbors, KNN, where K is equals to 5. And then from there, we have the 3 times crisis versus 2 times no crisis. As you can see, for the blue it is no crisis, and then this one is for the crisis, and then the new point is here. Okay, that is it. And then this one we say stores all the training examples. Prediction is equals to similarity search, that is the Euclidean distance after scaling. So memory grows with dataset, no learned parameters. And then KNN, the crisis record 79%, and also crisis precision is 88%. Higher recall, better at catching actual crisis, fewer false negatives. So this is preferred when missing a crisis is costly. Then when you come to model-based, so here we use the logistic regression. So this is the formula. So we use the sigmoid squashes output to probability between 0 and 1. So that is the decision boundary, this one, this line here. So no crisis side, and also the land weights, the systemic crisis like that, and then this one stores only the land weights. Prediction is equals to apply, then we have the sigmoid sign there, then from there we pass the weight, then we transpose those weights, then we multiply by the data, that is x, plus the bias. So that is first, constant memory. So this one it's interpretable positive weight. So this one raises the crisis probability. So logistic regression, the crisis recall is equals to 74%, and crisis precision 93%. So higher precision, fewer false alarms. Weights are interpretable, so preferred when explainability matters to stakeholders. So let us demonstrate this one with the code. KNN, find the 5 country years most similar to this new one. If 3 of them are crisis years, predict crisis. That's it. So let us run it in the Colab. So as you can see here, we have the instance based, so K-nearest classifier, so neighbors classifier. Then from there we have the confusion matrix and others. So the first thing that we do is we use the pipeline, that is where we pass the standard scalar, and also for the CLF, so that is the classifier. This is just a name, the ones that you can be able to use. So make sure that you have the names that are good, so but you can name the way you want to name them. Okay. And then for the K-neighbors classifier, so this one we provide the number of neighbors, that is 5, so which find the 5 country years most similar to this one. if most of them had a banking crisis, predict crisis, like that. Okay, so when you click there, so note the scale. So KNN uses the Euclidean distance, so features on different scales. Inflation in percent versus binary flags would be completely dominated by large-scale features. Scaling is mandatory. So here the crisis, the recall, it is 79%. And the precision, that is the crisis precision, it is 88%. Okay, so then the next thing that we need to do, we need to see the logistic regression coefficients, so which we need to draw a bar, so which we're gonna come just here. So we need to come to this part. Okay, so in this part, so we have the coefficients where we use the data frame. So for the feature, we pass the feature columns, then the coefficients, we use this one, the LR model, this one. Okay, and then from there, the next thing that we do is that we set the ascending order, we sort them with the coefficients. So then the ascending, we set it to false. Okay, and then from there we just draw them, and then from there all those things are just for matplotlib. Okay, so when you come here and you run it, you can see how it looks like. Okay, now look at what the logistic regression does. After training, all the information from 800 rows is compressed into 7 numbers, 1 coefficient per feature. Positive coefficient, that feature increases crisis probability. Negative, it decreases it. Look at which features dominate: systemic, crisis, and currency. And inflation, annual, CPI have the highest positive coefficients. That makes economic sense. KNN can never tell you this. It has no coefficients to inspect. Model-based learning is interpretable by design. Next, now we can run this one for, and also you can use to predict using that one for logistic regression. You can see them there. Okay, and then from there, now we need to have these confusion matrices. So let us first of all draw them. So we just use the confusion matrix display.from estimate. Okay, so first of all, you pick for KNN and also for the batch pipe. Okay, and then the others are just for plotting and labeling. So let us compare them head to head with confusion matrices. The modern sklearn way, using confusion matrix display.from underscore estimator, this replaced the deprecated plot underscore confusion underscore matrix function. KNN has a higher recall on crisis, 79%, catches more actual crisis but lower precision, so more false alarms. Logistic regression, so lower recall, 74%. This one, 74%. When you come here in the confusion matrix, so misses more crisis but higher precision, fewer false alarms. For a central bank, which Which matters more? Missing a real crisis is far more costly than a false alarm. So recall wins. In this domain, KNN is arguably the better choice, purely on this metric. This is why domain knowledge must drive metric selection. We'll formalize this on chapter 3.